Dean first, other people, please keep your hands up.
Just a question about the your musical, the analogy with the signal processing. I don't think I understood it.
Okay.
The extent to which it is a constraint. It doesn't seem like what we normally mean by a constraint in that case. I mean, it's more like something like analytic continuation, a function here that can continue it there. It doesn't seem like a physical constraint in the sense of you restricting degrees of freedom. I mean, maybe you could say something more.
I'll say something more. Yeah. It's not nothing to do with analytic continuation. That's, I can tell you that. What it is another way to see it is, I posed it is if you give the data. Let me see if I can go back to the slide. There's no power to explanation. I'm extremely limited today. Right. If you give data at each of these points, all along the line, more or less, then you've specified the function everywhere. So that's a constraint. I mean, you're completely constraining the data in between. Does that make more sense than the way I put it before?
It does. It still doesn't seem like the kind of constraints that you're talking about elsewhere.
What did I talk about? Which ones?
The other.
That was. I thought that was my only example, really. So.
Well, the topological ones, right?
Oh, then it's different from the topological one, right? Definitely. Mm-hmm. Two completely different kinds of examples. I thought it'd be useful to have at least a couple different sorts of things in the air. Other questions?
Kim.
So can I see your space-time diagram real quick on the beginning?
Yeah.
You mentioned that that's not a particularly exotic constraint, so I'm gonna force you into something exotic here. So I'm gonna leave the whole.
Which one?
The next one.
The next one.
Here's a scenario. These are light years apart, like something I like to do. There's entangled protons.
What are they?
Everything's like this light years scale.
Everything?
Yeah, and
This and this?
and there are two entangled protons coming from lambda. But what the detector's hooked up to is a neutrino detector coming from neutrinos beamed almost at the speed of light from the far left here. Okay, so now what you're looking for
That's in view.
is an all-local constraint to link the light years away neutrinos with the protons. So it doesn't. Okay, so that seems difficult to me. But there's a clear link between the neutrinos and the detector, and there's a clear link between the proton and the detector. And so now you basically reapply the zigzag argument that led you to looking at lambda in the first place.
I used the zigzag argument?
Well, no, the original argument that you started with that sort of motivated looking at statistical independence.
Okay.
And now just putting a constraint between these things at this time seems far less natural to me than linking it through the neutrino and through the proton.
It seems less natural. Oh, did you deny that there's a constraint then?
Well,
Or do you just think it's not a particularly useful?
What it could possibly be, given there's nothing there. Hard to envision what sort of constraint can link this light years away neutrino with this proton far over here.
Right.
But it's a lot easier to picture the link going on that part.
Well, I think the other thing you have to think about, that I think about it with this, and this goes very underanalyzed, is that these kinds of preparation, certainly the state preparation here, and any situation in which you're going to have a detector sensitive to a single neutrino, are extremely low entropy events. Right. I mean, this is sort of effectively a measurement of the neutrino. And I don't think you would ever expect, this is why these experiments are hard to do. So these are extremely special sets of initial conditions. And my thinking is that you're only going to get interesting correlations like this when you have in those setups. The only thing which you've added to this is you've added the neutrino.
Yeah.
Right. I mean, you're conceding that the preparation of the entangled state is special. Right. Yeah, and then the question is well, how does this neutrino affect factor into the non-local constraint, so as to give rise to the result. Yeah, I don't know. But I also think it's kind of equivalent. I mean, I don't, so are you suggesting that it's just not as, well, I think it's not kind of equivalent, is equivalent. So is your thinking that your heuristic is easier to use and doesn't suffer from the same problems?
Well, there is something along the neutrino world line, and there is something along the proton world line. There's just nothing.
Well, there's a neutrino along the neutrino world.
Yes,
so
right, and there's nothing along the surface you're interested
There's nothing along the surface.
Well,
There's a
minor
detector, a
surface
neutrino, and a
Right.
pair of protons,
Yeah.
and another detector.
Right. So that's just, it's a concern.
Yeah.
I've got a finger on this point.
Uh-oh.
There's a familiar context in which we have a link between something like a non-local constraint and causality, and it's the connection labelled by the Reichenbach's principle of the common cause. It tells us when we've got some sort of non-local correlation, we should look for a common cause in the past.
Right.
Now, my suspicion, and the suspicion increased by Ken's comment, is that in effect that's what's going on here. It's just that, so that this picture is not as different from a retrocausal picture as you think. It's just that rather than focusing on the kind of causality bit, the bit that Reichenbach tells us we're entitled to focus on in the ordinary cases, you're just focusing on the correlation itself. But really it's the same story. And so Ken's, it's not an objection, it's just pointing to the fact that in these retrocausal cases,
Right.
we get the same kind of explication as we get in the ordinary common cause cases, it's just that it works in the opposite direction.
Okay, yeah, that's interesting. It's let me say a little bit more about that because it just provokes something I didn't really talk about. I mean, the problem with both, I wouldn't say the problem, but there's an element, this is a little bit ad hoc as I stated, right? Because this is, I'm claiming there's a constraint, but I haven't, a true constraint is something that's going to hold at every time. Like if I wanted to turn this into a law that shows that quantum mechanical effects happen all the time, then I want a constraint, just like the Gauss law constraint, those constraints are conserved. They hold now, they hold before, same functional form, the matter can rearrange itself. So the correlations, as you say, are kind of, they're already there, they're always there. And the way I'm thinking about it, maybe this makes some connections with retrocausality, is that what you're doing when you're doing like an EPR type of experiment, you're preparing a very special entangled state, trying to keep everything else out of the way, is you're probing these non-local correlations. That's what you're doing. It's very hard to do. They generally hide themselves. That's why it generally looks like we have independent degrees of freedom here, 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 and here. But in special situations, you can probe the non-local.
Okay, so this is where the difference in outlook is coming in, I think. Because
Okay.
from the retrocausal viewpoint, you're not probing them, you're producing them. And so it's the fact that you act in a certain way at the top that ensures that this earlier non-local constraint is satisfied.
Right, and then I guess my worry would be, well, what's to ensure that quantum mechanics holds all the time? Like, in other words, what's the... you're producing something, but is it going to be the right thing?
Well,
In other words,
that's the laws. I mean, just as when you act and you produce one of these correlations in the future, you say, well, what is it that ensures that this constraint, which you can map from time to time, is always going to hold? Well, it's the laws.
Right, well, I mean, you need this thing would need to be preserved by the dynamical evolution. I'm not sure, so how do the laws fit into the retrocausal? How do the laws ensure?
Well, I mean, it's going to depend on the particular case, but if it's the neutrino case, there'll be some property of the neutrino which ensures that it doesn't change its relevant property.
Okay.
But again, I mean, all the story is going to go backwards because it'll be those laws, whatever they are, will get you from the fact that you pick a particular measurement setting at the top to the fact that this correlation holds at the earlier time.
Right, well, when you think of a charged particle moving backward in time, does it radiate, and if so, in which direction?
I'm not thinking of them as moving. I picture they're just world lines.
Well, fair enough, but I mean, you have an electron, a world line, and if it's accelerating, it's going to radiate.
I think we're getting into a different debate there. About the
this is part of my this is part of why I've resisted the retrocausal picture, but yeah, I do agree.
Okay,
It's going to go up.
so I think there's more that we should talk about.
Yeah.
This is just supposed to be a...
Should I point the laser pointer at the next question?
It's Tim.
Well, I think I'm going to pass actually, because I think it's sort of being captured there.
Okay, in that case, Peter, you're...
No, you said what it was.
Wow, good.
You've almost said so,
Rephrase it.
if you're happy with these non-local constraints, why not just apply a non-local constraint to the outcomes and get it by violation? That seems to involve much less complex explanation than a non-local constraint that applies to the violation.
You want to apply them to the outcomes. Well, because I suppose because you're going to then disconnect the outcomes from the original state.
Yes, you've got a new mechanism for generating correlations. Yeah, don't even need the common cause, you've just got a non-local constraint. It's like I mean, if you're happy with it to generate correlations down here, why not use it to generate correlations right at the moment they're actually needed?
Let's see, I thought I answered that. I mean, that sounds actually like quantum mechanics. I mean, quantum mechanics violates outcome independence, right? So a theory that just works on the outcomes and insists on non-local correlation. One such theory is quantum mechanics, right?
You might actually do that.
Yeah, and then you might, and then so, but then that sort of, raises the question: well, what the hell is wrong with quantum mechanics? What are we trying to solve here? And quantum mechanics works. But we're looking for a kind of a realistic picture. So that was the hope that this would provide, something like a realistic picture of what's going on prior to measurement, not just something that makes the measurements come out right. But it does, the subtle thing about it is that measurements are in some sense, and I think this is one of the things that might have bothered Bell, that when the measuring device and this applies to all these analyses, and the state of the particle are not independent, then what is a veridical measurement? Right? I mean, what do you're not really, the measure, you're not, well, you're measuring a pre-existing property of the particle, but the pre-existing property is a function of the way you've set up, a partial function of the way you've set up the measuring device. Okay, I don't want to undermine my idea any further, so.
Thanks.
Sorry, I'm not quite understanding the notion of non-local constraints. So I was just wondering if you could explain how, just another go for the slow, how this relates to the waveform case, because you said that you had the picture of the wave, and then you said that the bit in the middle is determined by the bits either side, right? And then you said one's the mu A and the other's the mu B.
Yeah, that was a loose analogy, right? It was different, right? It's a picture, so there you have a temporally
yeah, but I mean, a wave that it is not changing over time. It's not a wave, right?
What's that?
It's not a static structure, is it? I mean, you've got a representation of it as a static structure, but it's, so the two bits of the wave, they aren't both in the backwards light cone of the bit in the middle.
Right.
Right, but here,
Yeah, the wave is a function over time.
yeah,
You know, it's a f of t, this is a f of x. So the analogy requires, yeah.
it's just that it says a causal past. I thought that the non-local constraints were constraints on the causal past.
They are.
But they're not in the way.
The idea, so just the simple idea is, if this function, that whatever describes, you know, is a multi-dimensional function, but if that data is band limited, then it can't be freely specified. Okay, so take the Fourier transform of all this and put a cap on it as far as what the frequency components, the power spectrum looks like. Then, in that case, this data is not going to be freely specifiable. One way to think about it is that a sufficiently fine grid capturing the amplitude of whatever this function is at every point will dictate the values and all the other things.
Okay, and
That's
that's
how it's
on some space-like hypersurface.
Yeah.
Okay.
Okay, we have time for perhaps one more question, if there is one. Otherwise,
Nobody wants to obstruct the path to refreshments. I applaud you for that.
you can see that point. So
Okay.
please join me in thanking you.